ईयर स्टूडेंट्स, अगर आप इन वीडियो लेक्चर्स का मैक्सिमम यूटिलाइजेशन करना चाहते हो तो आई थिंक आपको ये इंप्रूव सेशन डेफिनेटली फॉलो करना चाहिए और रिलीजियसली फॉलो करना चाहिए। इंप्रूव सेशन क्या है, इसका लिंक डिस्क्रिप्शन बॉक्स में है, तो जाओ उसको चेक करो। इसके अलावा अगर आप व्हाट्सएप ग्रुप ज्वाइन करना चाहते हो, और मुझे लगता है आपको करना भी चाहिए, तो आप क्या करो, हमारे वेबसाइट पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो या फिर इस व्हाट्सएप नंबर पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो, सो दैट हम आपको उसमें ऐड कर सके। चलो अब पढ़ना शुरू करते हैं।
Welcome back. So this is the problem solving in work power energy, and we'll start with this like simple problem. A block is kept on the ground. The ground is not smooth, and the coefficient of friction is nu, and it is pulled by an external force F at an angle of theta with the ground. Okay, and it's given that the block is not being lifted off the ground. That means your F sine theta component is less than mg. Okay, and you have to calculate the work done by that external agent and the work done by friction as a function of time. Okay, so assume in time t the block is going to travel a distance of x, or this is basically displacement as well because the body is traveling a single dimension. Okay, so let's figure out first the value of this x as a function of time. So we have this formula, s is equal to ut plus half at square. Okay, and u is 0, so it just boils down to s is equal to half at square. Okay, so let's first figure out the acceleration. If in this case I'm going to assume that the block is moving. Okay, so the sliding is there and the maximum friction is going to act. So acceleration in this case, acceleration will be f cos theta, the horizontal component, minus the maximum frictional force divided by m. Okay, here f max, now your f max is nu into n. Okay, in this case for the normal reaction component, if I'm going to draw the FBD, this is going to be f sine theta, this will be f cos theta, this is mg, this is n, and something like this is given by friction force. From the vertical equilibrium I can say that the normal is going to be mg minus f sine theta. Okay, so this f max is going to be nu and n is going to be mg minus f sine theta. This is your f max. Okay, so in this case the acceleration is going to be f cos theta minus f max, that's basically nu mg plus f sine theta divided by m. Okay, so just notice that I'm taking the negative of f max, so this becomes minus nu mg and then plus nu f sine theta, nu f sine theta. Okay, so this is my acceleration, and again I can rearrange it in this way. I can write f cos theta plus nu sine theta minus nu mg, this whole thing divided by m. This is my acceleration. Okay, so my s is going to be ut plus half into this value, that is f cos theta plus nu sine theta minus nu mg half into, this is my a into t square. Okay, so this is my displacement as a function of time. Now I just have to take the dot product of the corresponding forces, so I'm just going to take this value as this whole thing is constant. Okay, so f cos theta plus nu sine theta minus nu mg by m is constant, so I'm going to write it, just alpha t square. So the alpha is this whole value. Okay, so this whole value is constant. I'm just going to keep it alpha. In general case the values of these forces f, theta and nu will be given, so it will be very easy to calculate this alpha. For the timing, just to save me some time, I'm just going to call this whole guy alpha. Okay, now the work done by f guy is going to be I can take f dot ds, so f into this displacement into cos theta, so it's going to be f alpha t square cos theta. Okay, and similarly, and again keep in mind this is going to be positive, and similarly work done by friction is going to be the frictional force into this displacement, and since that angle is going to be 180 degrees, it's going to be negative, so I'm already going to add this negative alpha t square, this displacement, and the friction is F max. F max is nu mg minus F sine theta. So this is nu mg minus F sine theta. Okay, so again this nu mg minus F sine theta is like again another constant, so you can like this multiply this alpha and this whole thing and make it another constant beta or some sort of that. Okay, so again this is my answer, and this alpha value is taken from here. Okay, let's move on to the next problem. So okay, so in this case you're supposed to find the work done on both blocks and work done by friction on both blocks, and given external force is equal to 20 Newton. So let's first analyze the system. So we have a block of 2 kg mass and a block of 3 kg mass, and the lower surface, the ground surface, is frictionless, and the surface between these blocks is having a coefficient friction of nu is equal to 0.2. okay, and these 2 and 3 kgs are the masses of the bodies. Okay, so the first problem says find the work done by friction on both blocks given that F external is 20 Newton. Okay, so in this case you have been given the force, so to find the work done by friction you have to figure out the value of the friction, okay, and the corresponding displacements. Now here's the trick. If these guys are moving together, okay, so this 2 kg and 3 kg, if they are moving together, the displacements in given time is going to be same. Okay, and if they are not moving together, they are going to undergo a different displacements. So if I'm supposed to find the work done and given F is equal to 20 Newton, so I'll have to figure out displacement. So suppose the time interval is given 2 seconds. So for both cases it's 2 seconds. Now let's talk about problem number 1. Here the maximum friction that can act between 2 and 3 kg block is nu into n. Okay, n is 20, so 0.2 into 20. Okay, and in this case, if I'm talking about the maximum friction, then I can also calculate the maximum possible acceleration of this 2 kg guy. Okay, so it's going to be nu into n divided by its mass, that is 2. So this becomes 0.2 into 10, that is 2 meter per second square. So this is the maximum acceleration that this 2 kg block can have. Okay, now let's say in these kind of problems always assume that the system is moving together and see if friction force is sufficient for that motion or not. So if I'm going to assume that these guys are moving together, so this ground force is not exerting any work, and this friction force, like this will become internal force for this 2 kg and 3 kg block, and it will go to 0. So net force F net on system is going to be 20 Newton. Mass total is 5 kg, so A system is going to be 20 by 5, that is 4 meter per second square. Okay, so if these guys are moving together, somehow they're going to move with a common acceleration of 4 meter per second square. But here's the trick: the maximum acceleration that this 2 kg block can have is 2 meter per second square. That is corresponding to the maximum friction that can have. So 0.2 into n is going to maximum friction divided by 2, that becomes 0.2 into 10, 2 meter per second square. So this 2 kg block can have a maximum acceleration of 2 meter per second square, and I want it to move with an acceleration of 4 meter per second square, and that's not possible. So these guys are not going to move together, they're going to move with different acceleration, and on 2 kg block the maximum friction will act and the sliding will happen, it will move in the forward direction. So this 2 kg block, since it's moving forward, the friction has to be F forward, and on this 3 kg block the friction has to be backwards. Okay, and this value has to be maximum friction. Maximum friction is nu into n, and that is 4 Newton. Okay, you should be able to see from here 0.2 into 20 is 4 Newton, and again this is also going to be 4 Newton. F is given as 20. Okay, so acceleration of this 2 kg block is going to be 4 by 2, 2 meter per second square, its maximum acceleration, and acceleration of this 3 kg block is going to be 20 minus 4 is going to be 16 divided by 3 meter per second square. Okay, so work done by friction in this case is going to be positive because friction is acting forward and the acceleration is also forward, so displacement, corresponding displacement is also going to be forward. Now let's to find the work done, we also have to find out the displacements of these guys in 2 seconds. So let's calculate the displacements. displacement of the 2 kg block S2 will be S is equal to ut plus half at square, ut is 0, so half into a into t square is 4, so this is going to be 4 meter. And similarly I can calculate displacement of this third guy, 3 kg guy, half into a into t square is 4, and this is going to be 32 by 3 meter. Okay, let's check the calculation. Half into a into t square. Okay, yeah, it's correct. So work done by friction in this case, since friction is forward, displacement is also forward, force into displacement, so 4 Newton into 4 meter is going to be 16 joules, and again positive. Work done by friction in this case, friction is acting backward, displacement is forward, so like cos 180 is going to be -1, so 32 into 3 this displacement, and the force is 4 and with a negative sign, so this is going to be 4 into 8 128 divided by 3 joules. Okay, so this is the answer. Let's move on to the next problem. Okay, let's now do the part B. Repeat A if F is equal to 10 Newton. Okay, so again I'm going to repeat the calculation. I'll assume that these blocks are moving together under this force, and then I'll see if that acceleration is a feasible acceleration or not. Okay, so if F is equal to 10 Newton, again this taking this whole 2 plus 3 body like as a single system, the acceleration of the system, if they're moving together, has to be 10 divided by 5 is equal to 2 meter per second square. So if F is equal to 10 Newton, they're going to move together with acceleration of 2 meter per second square, and that is feasible. As you should be able to see from the previous calculation, the maximum acceleration of this 2 kg block is 2 meter per second square. So if the system wants to go with an acceleration of 2 meter per second square, this 2 kg guy should not have any problem. So in this case, if F is equal to 10 Newton, this both 2 plus 3 kg guy are going to move forward with this common acceleration 2. Now if the acceleration for both guys is same, displacement of second and the displacement of third is going to be equal. Okay, and friction like friction on 2 kg guy is going to be negative friction on 3 kg guy. So what we have here, without even doing the calculation, I should be knowing that work done by friction on the 2 kg guy has to be negative of work done by friction on the 3 kg guy. Why? Because the displacements are same, but the direction of friction is different on both guys. Okay, so in one case is going to be positive work done, and in one case is going to be the negative work done. So let's just quickly calculate the displacement. Displacement in time t is going to be half into a is 2 and t is 2, so it's going to be t square. So this is again 4 meter, half into a into t square, 4 meter, and friction. So if this guy is moving with the maximum acceleration 2 meter per second square, that means maximum friction is there. Okay, so F max value, again it's nu into n, and this is nu into n is 20, and that gives you 4 Newton. Okay, so F max is 4 Newton, so work done by friction on this 2 kg guy is 4 into 4 is 16 joule. Work done by friction on this 3 kg guy is minus 4 into 4 is minus 16 joule. Okay, so in this case, work net by friction on the system is 0. Okay, so friction is not doing any kind of work, and if I'm talking about the kinetic energy of the system, it remains constant. Okay, so if this F is not changing, the kinetic energy of the system remains constant, because the system is, the friction is not doing any work on the system. This is different than the previous question, where there was sliding and the friction, work done by friction on the system was non-zero. So work done by friction on the second guy, the modulus was not equal to work done by friction on the third guy. Okay, or even you're going to add with the signs, they're not going to be like, they're not going to sum towards 0. Okay, now I hope this made sense. Let's move on to the next problem. Okay, so here's the next problem. Suppose you have a mass m and it is at a height of h from a pan, and that is connected to an ideal spring, and that in turn is connected to the ground. Okay, so this pan is assumed to be massless, and this spring is also ideal. So initially there won't be any elongation or compression in this spring. Okay, so there is no deformation, and we have a mass at a height h from the pan, and it is released from rest. Okay, so if block is released from rest above the pan, what will be the maximum compression in the spring? Assume block sticks to the pan and no other energy losses are there. Okay, so this is the simple scenario of conservation of mechanical energy. Why? Because the only forces doing work are the gravitational forces and the spring force. Okay, and both of them are conservative in nature, so the total mechanical energy of the system remains constant. Okay, so what I'm going to do, I'm just going to calculate the decrease in gravitational PE. So suppose the block goes from here to, and the final compression happens somewhere here. Okay, so this is my final block position, this is my final pan position, and somewhere here, like here is going to be my spring. So the compression in the spring is going to be this distance, let's call it x. Okay, or maybe x naught, because I'm talking about the maximum value. Okay, so this block comes from this point to this point, so the total change in height of this block is going to be h plus x naught. So that's equivalent to saying the decrease in gravitational potential energy of the block going from point A to point B of the maximum compression is m into g into h plus x naught. So this is the decrease in gravitational PE. Okay, decrease in gravitational PE of the system, because this whole thing is massless, so we are not going to consider decrease in gravitational PE of this guy. Now decrease in gravitational PE from, like, at point A, Ke is 0. When the maximum compression is going to happen, again Ke is going to be 0. So there is no change in kinetic energy, so no part of the energy is going to kinetic energy form. It's just getting converted from gravitational PE to spring PE. So this decrease in gravitational PE has to be equal to increase in spring potential energy. Now what is this increase in spring potential energy? Initial PE of spring initial is 0. Now PE of spring final is going to be half into K into x naught square, because now x naught is the compression and potential energy of spring is half into K into that x square, where x can be elongation or your deformation. So I'm just going to solve for this value, mgh plus so this is mgh plus x naught is going to be, this is decrease in gravitational potential energy is going to be increase in spring potential energy. So this is just a quadratic function of x naught. I can solve it using like the roots of ax square plus bx plus c. Okay, so again, like this is the quadratic equation, and using this formula minus b plus minus root over b square minus 4ac divided by 2a, I can get the value of x naught. I'm not going to do it. Okay, now let's discuss problem B. Discuss how the calculation changes if pan has a mass of mp. Okay, so this was very easy. You just calculated the decrease in potential energy of the mass and you like equated it to increase in potential energy of the spring. So now this let's see how this equation is going to change if the pan is also having mass. So now in this case, now decrease in potential is going to comprise both of like change in potential energy of the block as well as the change in potential energy of the mass. Now assume, again I'm going to assume that this pan goes from point A, this is my point initial configuration, to this final configuration and undergoes a compression of x naught for the spring. Okay, now this problem might look easy or like very similar to the previous problem, but that's not actually the case. We'll see why. Now think about it. In the previous problem we just had one block like changing its gravitational potential energy. Now we have two blocks or two masses. One is this block and the other one is this massless the pan having mass of mp, so it's no more massless. Okay, now if this block is coming from here to here, or that is basically the position of this pan, this block undergoes a change in potential energy of mgh plus x naught, that is same like having the same form as the previous one. Now this pan is also changing its configuration in the gravitational space from this point to this point, so this is also changing or contributing to the total change in potential energy of the system. So total change in potential energy of the system, delta PE of the system is coming from delta P of this mass plus delta P of this pan. Okay, so this mass part is mg h plus x naught. Okay, and this span part is mpg x naught. Okay, so I hope this came easy. So this is basically the change, gravitational potential energy change in mass block plus mass of the pan. Okay, now here comes the interesting part. If I'm going to ask you what is the change in spring potential energy, what are you going to tell me? Is it going to be half k x naught square minus 0, and where x naught is going to be the final compression? That's incorrect. Okay, why? Let's see why. Here, if this pan is going to have some mass m, this spring already has some compression, because if this pan has to be in equilibrium, there has to be a force coming from downward in the direction upward to balance its own weight. So if I'm going to draw the FBD of the pan, there has to be Fs that is going to balance this MP into G. Now this Fs has a form of K into X, where X is the elongation or compression in the spring. In this case, this Fs has to be upward, so this spring has to be compressed. In that case, Kx has to be Mg, or this is Mpg, or Xi, the initial compression in the spring, is Mpg divided by K. So let me write it down. This is the initial compression of the spring. Okay, now if this pan goes a further like compression of x naught, so in this initial situation, when I'm going to drop this block, and this is the case, and this we have this MP and we have this M, this spring is not in its natural length, it's already having a compression of xi. Okay, so suppose the natural length of the spring was somewhere here. Okay, this was your xn natural length, and because of this MP, it already underwent a compression of this guy, so this is your xi. Okay, so in this case, the change delta PE of the spring is half k xf square minus half k xi square. This is the like increase in the spring potential energy of the spring, where xf is the final compression or a final deformation, and xi is the final deformation or the final elongation or final compression. In this case, xf, what is the value of xf? Try to figure it out. What is the final compression in the spring? Let me tell you that. Pause the video if you want to figure it out. What is the final compression in the spring in terms of whatever variable is given in like on the board. So xf in this case is going to be the initial compression xi plus the further compression. Further compression is x naught. So this is going to be xi plus x naught, and what is initial compression is basically given xi. So this equation changes to k by 2. xf is xi plus x naught square, the final compression, minus the initial compression. So this is the change in spring potential energy of the spring, and that has to be equal to the decrease in, or this is the increase in spring potential energy, and this is going to be the decrease in gravitational potential energy. So using conservation of you can say mechanical energy, you're going to write mg h plus x naught plus mp g x naught has to be equal to k by 2 xi plus x naught square minus xi square. Now again, if m and the mp and this m value and the k is given, you can directly calculate this xi value. So this xi is going to be known. Okay, and we have this again. This whole equation is going to be like in like a quadratic in x naught, like similar to the previous case, but the actual function is going to be like a little more complicated. But again, this is just a functional form of ax square plus bx plus c is equal to 0, and then you can solve for x, where here the variable x is your x naught. Okay, so this was like a slightly different variation of the previous problem, but the calculation is going to be a lot different. Okay, I hope this made sense. I'll see you in the next video where I'm going to discuss like the archive problems of work power energy. Stay tuned. Thank you.